Well, let's finish this section off with a little bit of IVT, better known as, or actually, no, it's better known as IVT. Sometimes people say the intermediate value theorem. Huh? Here we go. It's the intermediate value theorem. See, we don't actually write this ever. Intermediate. Oh, that's a long word. Value is not so bad. Neither is theorem. But for short, we just call it IVT. What's dope about this is you've done this in other classes. If you've ever taken an algebra class at Sierra College, I promise you've done it, unless your teacher just hates you. I'm kidding. Sometimes we miss stuff. I know I do. And before you can read this, have fun. Go read all that stuff. Yeah, I've given it to you. I've shown it to you. There's the intermediate value theorem, but I think maybe just showing what's happening rather than all the notation. I think that might work a little better. Okay, here we go. I'll make a dot over here. I'm going to say this is A. Of course, this is f of A. It's whatever the function's going to be. I'm going to say there's some function. And I also want to say that the function's continuous. Okay? So we have some function f is continuous. Cool. Wow, I didn't even put that dot anywhere near the b. Let me make the dot bigger. There we go. Bigger dots. And now it's actually at that spot. And then there's f of b right down here. Cool. All right. So normally I would have you in class make a dot above the x-axis, make a dot below the x-axis, and now connect the dots such that it's continuous, and don't touch the x-axis. Oh, by the way, the x-axis is where y equals 0. Okay? That's where y equals 0, or f of x equals 0. So let's draw it. Oh, don't touch it. Oh, shoot. I had to. That's the intermediate value theorem. If you have a value that makes your function greater than 0, and you have a value that makes your function less than 0, then gosh darn it, there's got to be something in between, some value in between a and b. I don't know, maybe some c, such that that function equals 0. Let's try it again. Make a dot and a dot. Now don't touch the x-axis where y equals 0. Now it's a, and that one's f of a, and this one's b, and this one's f of b, and don't touch the. Well, I don't know how to do it. It has to, and that's the theorem. It's saying, well, somewhere it has to touch. Look, I made it touch 3 different times, because if f's continuous, then you don't have any choice. But this is actually what our theorem says. Bigger than an algebra class. Bigger than an algebra class. It's saying that if you have some line, it doesn't really matter where it is. Like y is equal to, I don't know, some number m. Who gives a shit what the number is? Maybe it's 4. Maybe it's 3. And you put a dot above it, and you put a dot below it. And if you connect the dots, somewhere in between a and b, we're going to have to cross over where y equals m, right? It doesn't have to be 0. Right? It could be like, oh, that's not a function. I screwed up. I wouldn't have passed the vertical line test. Okay, maybe like that. Okay. Dang. So it works for any of them. So now let's go back and let's read all the nonsense. Suppose f is a continuous function. That's big. The continuous function part, when we do these problems, we must state that it's continuous. So this doesn't make any sense. Because who gives a shit? Like, not continuous. Prove that it goes through the x-axis and it's not continuous. No, I don't have to. Maybe it goes like this. It's not continuous. Maybe it's just got some asymptotes there and it never touches. That's why that shit has to be continuous. You have no choice for us to make a statement that strong. So we say if it's continuous and you're on some closed interval, right? In between 2 points. Look at my closed interval between a and b. Between a and b, look, it even achieves it. I filled in those big ass dots. Then let n, I used m, be a number between f of a and f of b. Man, we're going to use 0. Our number is going to be 0. Down here, I chose it to be something else. I don't know. So as long as we know there's some number that's in between that f of a and the f of b, we know there's some value in between that's going to make it equal 0, or that value of n or m or whatever it might be. Now, the intermediate value theorem does not solve for anything. It does not solve for anything. We just show that there's existence of. And where it works really well is we have this function here, some cubic, x cubed minus x minus 1, and we claim that it's equal to 0. Okay. Well, good luck. I'm pretty good at algebra. Yeah, I don't know. I think I'm pretty good. I toot my own horn there. I think I can do some pretty good algebra. I don't know how to algebraically solve that. I'd have to pull out a book and use like Cardano's law. Some random ass thing. I don't know how to do this, but I can sure as hell can show it. Now, let me show you the difference between an algebra class where you should have already done this and a calculus class. In an algebra class, we'll say, show that there's a root of the equation in between 1 and 2, such that this function equals 0. So we'll actually tell you what to plug in, and that's just telling you. Plug in 1 for x, plug in 2 for x, because we're going to take it aside and do this. Let's take whatever it is we want to set equal to 0, pull it aside and call it maybe f of x. Now, if we can show that we can get a positive value and we can get a negative value in between 1 and 2, well, then most certainly there must be some connection in between. There must be some value of c such that this function equals 0. All right, so what we're going to do is, since this one gives us the values 1 and 2, we'll be like, all right, well, f of and f of, let's see. Because we got to plug in 2 numbers. I like to just make parentheses and then figure out what you're going to plug in. We're like, oh, we're going to plug in 1. So we go 1, 1, 1. And then we're going to do 2 as well. 2, 2, 2. Cool, let's figure out what those values are. So 1 minus 1 is negative. I actually don't care what the number is. I know some of y'all are like, it's negative 1, it's negative 1. Don't care. I don't care. The value, that makes no difference to us. As long as it's negative. I'll write it down. It's negative 1. Don't give a shit, though. Like here, you got 2 cubed. That's 8. 8 minus 2 minus 1, that shit's positive. I look at this and go, the answer is positive. Because the number doesn't matter. We're not solving for anything here. We're just showing it exists. But I know it's going to drive some of you crazy. What's the number? The number doesn't freaking matter. 8 minus 3 is 5. But this one's positive and this one's negative. Which means our y values are both positive and negative. So wait a second. All we know is in between 1 and 2 for our function. At f of 1, we get a negative value. There's some point down here. And for f of 2, we have a positive value. It's up here somewhere. And we know that it's continuous. Therefore, there has to be something in between there. I don't know, some number. And we're never going to find out. It doesn't matter. That somewhere along here, it touches. So now we say. Now here's the big piece. You got to say this at the end. They'll probably have you write this one out on the test. All right. So then we can say, therefore, 3 little dots means therefore. We're about to say something cool. Since f is continuous, this must be written down. This is the huge part. If it's not continuous, we can't say any of this. There we go. By IVT. And then we just restate this right at the beginning. Oh, wait. Hold on. I gotta write something. There exists a c in the interval between 1 and 2. This just means that there's a c in between 1 and 2. That's fancy talk, okay? Such that f of c equals 0. And then we can just end our problem. Getting used to this. So we wrote this out. This is a super cool calculus student now. We say, since f is continuous by IVT, there's a c value that's in between 1 and 2. That's just another way of writing it. That's a fancy way. If you just want to write it like this, go for it. You don't need to write both. So there's a c in between 1 and 2 that makes this function we just had equal 0, which also implies that that equals 0. So there it is. That's what we'd write. And I know a lot of students get intimidated by the fact of how many words there are. Since f is continuous by IVT, there exists a c in the interval between 1 and 2 such that f of c equals 0. Holy crap, you sound pretentious. But we got to get used to this crap. We got to be able to read it. We got to be able to play the game. I don't like talking like that, but I know how to play the game when I have to. All right. Here's a good one. Here's a good one. So let's go get this thing. Now this is a calculus level problem. This is one There's no interval given to you. It's up to you. You might have to guess and check. So our first game is we're going to want to set this thing equal to 0. Let's move it on over and set it equal to 0. So we get the square root of 2x plus 5, and we move everything over, equals to 0. Cool? We just subtracted 4 and added the x squared. So we can get it all off to one side. So we don't want to set it equal to 4 or 3 or 2. Let's just get it positive and negative and move on with this shit. So I'm going to now let f of x just equal the shit that's on the left-hand side. Go! We're okay, we're okay. Now, we have to kind of come up with some values. So a little bit of guess and check. But first off, we got to think about this. It has to be continuous on the numbers we choose. -4 is continuous everywhere. X squared is continuous everywhere. But this, the square root of 2x plus 5, that is not continuous everywhere. We'd actually have to jump aside and be like 2x plus 5, that shit's got to be greater than or equal to 0. Right? Because no negatives underneath an even root, right? So we divide by 2 and we're like, oh, our x values have to be bigger than -5 over 2 or -2.5. That's going to keep everything, the radicand, the shit underneath the radical, the stuff underneath the root, that keeps all that 0 or bigger. So we can only choose values that are bigger than -2.5. So don't choose anything else. So to save you some time, because you're going to run through and look at a few of them, there's going to be a couple cool ones. And you should always start with one number. This is where I start every time. I'm just going to get a baseline. I'm going to figure out what happens when you plug in 0, because 0 is the easiest shit. Like you get the square root of 5 minus 4. And you're like, is that positive or negative? And you're pulling out your calculator, and I'm just shaking my head sadly at you. Come on. Isn't 4 the square root of 16? So what do you think is bigger, the square root of 5 or the square root of 16? This shit's less than 0. It's a negative. So we think of it, we're like, boom, we got the negative, we got below the x-axis. And now we're like, well, shit, we want to get something that's going to be above the x-axis. But just look at the damn problem. Bigger x's, bigger answer. Bigger x's, bigger answer. Oh, shit, let's plug in some bigger x's. And I don't know, I don't want to go to 1 and find out it doesn't work. I'm going to go to 2. Shit, I could just plug in 37 or something and go like, oh, look, it's greater than 0. It's positive. But we won't. Like, all right, so 2 times 2 plus 5 minus 4 plus 2 squared. Oh, shoot, what is this? That's going to work out nice. That's 4, 5, 9 squared. That's 4 minus 4 plus 4. That's equal to. It's equal to positive. It's 3. It's equal to positive. So we just showed that there must exist some sort of c in between the values of, now it's back here, it's these values here, between 0 and 2. I found some sort of closed interval between 0 and 2. Just by looking at it. Sometimes you have to create it, because you should know what these functions do by now. I know it's a sad reality that's probably not true yet, but we need you to get there. All right, so let's end it up, and now we got to do all the fanciness so we can say, therefore, since f is continuous, gotta write that. We called it f. Now, I can make this very quick. This is there exists a c in the interval between 0 and 2, such that f of c equals 0. See, that's the math way of writing it, where it could be very quick. Or we could say by IVT. And now let me write it a little different. Let me put it a little more friendly. By IVT. There exists, or there's a c, and maybe we write it this way, between 0 and 2, there's a c between 0 and 2 such that f of c equals 0. I don't like writing such that, st is the shorthand, and now we've answered it. So most important, we must write in that it's continuous, or else we cannot make that statement whatsoever. So as long as we have a closed interval, we can say that there's some c within the open interval. Don't connect those endpoints. That's going to make it equal 0. Trippy. Weird. I'll see you in the next one. That'll be 2.6. Oh, that'll be the good stuff that's really testable crap. All right. Later.